it is known that Fermi energy can be defined as it is the highest occupied energy level by the electron at the temperature T is equal to 0 Kelvin. And we have imagined that energy band. See, when you take a solid as a whole together, because of n number of atoms in it, we expect the energy band to containing a large number of closely spaced energy levels, almost equal to the n energy levels, and each energy level is separated by a small this gap of 10 to the power of minus 6 electron volts. So if you have a solid contain n number of energy levels, there will be a large number of closely spaced energy levels. So now, since the number is very large, very huge number, we don't know where exactly the electrons may go and occupy, may sit in the energy levels. So because of the availability of large number of energy levels. So therefore, we don't know. Then to find the number of energy, to find the presence of an atom or an electron in any given energy level, we use the Fermi factor. It tells us the property of occupation of any electron or particle sitting in its energy in any of the energy level. So now we know that according to Fermi factor or Fermi function, the electron is whether it's sitting or not, how much it is available in that particular state is given by the probable values. This is the probability. So now, since we have only the probability, we are not seeing how many electrons are there. It cannot be said in an integer, cannot be given by a number. So the Fermi factor never gives us the number of electrons that is there in any given state. It gives only the probability of occupation of any given energies electron in the given state. So to know the actual number of electrons, to know the exact or the actual number of electrons, here we use the notation N of EDE. So N of EDE represents the number of actual energy electrons in the energy range DE. Taken a small energy range in the energy band, within that small energy range, how many actual number of electrons are present can be calculated. So now, since we can't see how many with the naked eyes, we cannot count the whether it is present or there or not by usual numbers. Therefore, all the measurements are only the probabilities. Therefore, if there are n of e d number of electrons present in a given energy range, then it is equal to the probability of occupying and multiplied by the Fermi factor. Say, for example, imagine in a class containing 60, the class strength is 60 students. On that particular day, we cannot say, I don't see that there are 60 students are present. And according to our distribution of the class benches in the room, let us assume that there are 30 benches, and on each bench two can accommodate. So there are 30 benches, therefore 60 students can comfortably sit. On that particular day, let us assume that I see only there are only 40 students are present, 40 candidates are present. It means other 10 10 benches are empty, and they were unoccupied. So now here, whether it is occupied or not is decided by the density of the state set of E. That is given by the Fermi factor. See, the Fermi, see, I told you n of E dE is the actual number, practical value. How many is present is depends on the density of this available density of students sitting in the states. If the students sat on any desk, means it is available. Like that, look at here. I have considered an energy band, a small portion of energy, the range I have chosen here, E and E plus DE. I am choosing a small strip of energy, DE, the range between E and DE, E plus DE. Now I am trying to find how many electrons are occupied in this particular energy range. So now what I am doing is I want to understand how many electrons are there within the energy range E and E plus DE. So now you know that the filling up of energy levels, this take place. Filling up of electrons starts from the bottommost level according to Pauli's exclusion principle, and it is kept on filling up. And I have chosen only the range E and E plus DE. I am looking the shaded region. Within that region, how many electrons are present? That is N of E DE. So N of E DE represents some practical value. Whether the electron is present in the within the energy range between E and E plus DE, whether or not is present is decided by the Fermi factor f of E. So N of E is equal to the states available, that is given by Z of E into dE multiplied by the Fermi factor. The actual number of electrons, that is N of E dE. Okay, if that is the actual number of electrons, then how many actual is present? The density of states available. So N of E dE represents the total number, that is equal to the density of states available. How many states are available, how many disks are available, something like that. The f of E is the presence of a student presence. Then the filling up of electrons takes place from bottommost according to Pauli exclusion principle. Now within the range of energy, if you consider E and E plus DE, the number of states allowed per unit volume within the small region of energy space is called the density of states. You understand now? So there are so many states available. How many of them available is represented by the Z of E dE. The Z of E dE is equal to given by pi by 2 within the bracket 8 ma square by h square to the power 3 by 2 E power 1 by 2 dE. Here A represents the width of the potential value. You understood in the quantum mechanics in Schrodinger wave equation, the distance, the width of the potential value, isn't it? That is A here. And the corresponding energy in any given energy state is given by E equal to n square h square 8m A square. What is density of states? It is equal to, imagine, before entering the class, there are 30 desks. So 30 desks can be occupied by 2 on each. So totally 60 can accommodate. So here the desk represents the number of allowed states. The density of states represents the number of allowed states per unit volume within any chosen energy range E and E plus DE. That is called the density of states. That is given by this expression. In order to see this number of electrons that is occupied, I should have this density of states available, and whether it is present or not is seen by f of E. So here once again the f of E represents the Fermi factor. What is Fermi factor? It represents the probability of occupation of an electron in the any given energy states. So if the occupation is there, it is 1, f of E is 1, therefore that is added. If f of E is 0, that particular state cannot be counted. Therefore, the total number of electrons in the energy range E and E plus DE is given by N of E, that is equal to the product of the density of states with f of E. Now you know the expression for Z of E, that is the density of states. F of E represents the Fermi function. If you multiply these two together, and if you calculate the number of electrons per unit volume, so you need to integrate the over this integration represents, you need to consider all the energy levels from the bottom to the topmost energy levels. From the above expression, the Fermi energy EF can be square by 8m within the brackets 3n by pi into 2 by 3. So this is the expression for Fermi energy. That is, you got this expression by making use of the Fermi function and the density of states. So this is of expression Fermi energy. Now this contains certain constants containing h as a Planck's constant, m is the mass of the electron, pi is a constant, you know that, and a small n refers to the number of free charge carriers here. Okay, so if you assume you are estimating the Fermi energy of copper, then value of n is 8.45 into 10 to the power of 28 atoms per meter cube. If you multiply it with a above expression, EF is equal to 5.85 into 10 to minus 38 n to 2/3 See here, and if you want to express in joules, you know that is multiplied by 1.6 into 10 to minus 19. So you know that conversion of joule to electron, 1 joule is equal to 1.6 into 10 to the power minus 19 eV. So using this, you can calculate the Fermi energy. And again, you know that above expression EF is with respect to at 0 K. But if you extend for temperature greater than above beyond this 0 K, you will get this right this particular expression. EF is equal to EF naught within square brackets 1 minus pi square by 12 kT by EF naught. And as temperature is increased, the second term in the square bracket is going to smaller and smaller values. Therefore, it can be negated. Ultimately, what we have, the Fermi energy is approximately equal to the one calculated at the 0 Kelvin. Therefore, whatever is it is measured at the room temperature, that as well holds good at the 0 Kelvin also. So now another term, it is called the Fermi temperature. So now how to define Fermi temperature? It is a temperature at which the average thermal energy of the electron in a solid becomes equal to Fermi energy at 0 K. The Fermi temperature, it is defined as a temperature at which the average thermal energy of the electrons becomes equal to the Fermi energy at 0 K. So the Fermi temperature becomes now for 3 eV Fermi energy, the corresponding Fermi temperature will be 34,800 K. It's a very huge value. Therefore, this Fermi temperature is only a theoretical concept.